Why am I host 500? Hang on. Okay, how many minutes of leeway do you think we should give to the people arriving late from the pizza party?
0.
Okay, maximum brutality. We just start. Feels kind of harsh though. If the pizza party started late, it feels bad to penalize people for leaving a little bit late.
Maybe just give them till like 8:03 or something. Oh, sorry,
okay.
That's my time. 3 minutes past the hour.
Yeah. I like 3 minutes. 3 minutes seems diplomatic. Okay, I'm currently doing something that's a really bad idea, which is I'm making a last-minute modification to my lecture slides, which is guaranteed to backfire, but okay, I think that works. Erin, should I start whenever, or?
Yeah, are you recording to the cloud or your computer?
I don't know what I'm doing. I didn't realize I was recording.
Let me see if I can stop you real quick.
Thank you.
Okay, let me record. Ooh. Are you able to make me host?
Oh God, yeah, sure.
Okay.
Hang on. There we go.
Okay. Okay, go ahead.
Awesome. Okay. Right. Let's see if we can. Oh, hang on. Can you make me co-host? Or I need. Wait. Do I need sharing permissions? Okay.
All right, you're co-host.
Thank you. Why is the screen share not working? Sorry about this. Hang on, sorry, there's an issue with my privacy settings. So I'm gonna have to come back. Give me 1 moment.
Okay. Sorry, guys. We're still working out all the kinks with Pathable and Zoom. So thanks for being patient.
Okay, let's try that again. Can you now see my screen?
Yes.
Okay, perfect. Let me see if I can get rid of that. If I make this full screen. All right, can you all see that?
Mm-hmm.
You wouldn't lose anything. Let me collapse that. Okay, so sorry about the slight technical glitch there. Hopefully we'll get slightly smoother at doing this over the next couple of days. So first, welcome to the first, I guess, the first official lecture in the series of lectures that we're going to be doing that will hopefully covering the kind of major conceptual and mathematical foundations of the Wolfram physics project. So there'll be a kind of series of 4 lectures that cover the sort of more mathematical side of things that I'll be giving over the next few days. Then we'll have a couple of lectures given by myself and Max about more practical kind of software development type things and how to use our tool stack and how to actually get started using our kind of the research code that we've developed and all of the function repository entries that we've created for doing this physics project. And that will come kind of later on in the week. And all of that will, of course, be interspersed with kind of special topics lectures given by Stephen and other things that he's going to be up to. So anyway, without further ado, this is the first lecture that's hopefully going to cover some basic aspects of our formalism, introduce this concept that we call causal invariance that's fundamental to a lot of the ways that we think about these models and its relationships to special relativity, and maybe giving some hints towards the relationship to general relativity, but that's going to really be the topic of the next talk. But as this is the first in the series, I wanted to begin by doing what I think George Bush described as the vision thing. But as this is liable to be at least a little bit embarrassing, I promise I won't take more than a few minutes of it. The basic idea is, so for the last, as Stephen kind of alluded to in his keynote, for the last 350 years or so, since the time of people like Newton and Galileo and Descartes and Kepler and others like that, there's been kind of one key methodological idea in the exact sciences and in physics in particular, which is kind of, you go outside and you find some phenomenon that you want to try to explain, like celestial mechanics or electromagnetism or, elementary particle interactions or whatever. And then you try to drill down and find the primitives and find the fundamentals from which you can then build up a quantitative mathematical model. What we're trying to do is kind of the complete inversion of that. It's a paradigm that was first really proposed in a serious way by Stephen back in 2002 with the publication of his book, A New Kind of Science, where instead, the idea is rather perversely, instead of starting from the phenomenon, drilling down and finding the model, you kind of start from the model and you build up and you basically enumerate spaces of possible models, and then you explicitly compute their consequences and attempt to do the analysis to figure out whether there is actually overlap between the things we understand in these models and what we know of actual existing mathematical physics. So the basic idea behind our formalism is to develop the most minimal structure which you can use to represent candidate laws of physics. Actually designing a data structure that is capable of representing a candidate universe is a highly non-trivial activity, and we're not convinced that we have the right model. But it's becoming increasingly clear that the model we do have does still have a lot to say about fundamental physics and about a lot of other things besides, as Stephen already alluded to. So kind of the basic underlying idea is treat space not as a continuum, but actually as a very large collection of discrete points with an adjacency structure defined on them by by essentially a network structure. And then you can represent possible dynamics on those candidate universes in terms of transformation rules between subgraphs in those networks. So each possible transformation rule effectively corresponds to a different candidate for the laws of physics, a different candidate universe. And then we can just enumerate the space of all such candidate universes, and we find beautiful things like these. And so essentially, the big question we want to ask is, could one of these be our universe? Could our universe be just lying out there in this computational universe of all possible universes? And that's a pretty difficult question to answer, and it's not immediately clear what the answer is going to be. But the remarkable thing that we've discovered over the last several months is that there exist large classes of these transformation systems, of these network-based space-time systems that are provably compatible with many aspects of known kind of mathematical physics, including special relativity, general relativity, quantum mechanics, quantum field theory in certain continuum limits. And we're immediately sort of being presented with a bunch of really neat correspondences between concepts like path integrals and the Einstein-Hilbert action in both quantum mechanics and general relativity, correspondences between global changes of dimension and inflationary cosmology, as well as a bunch of implications for things like the ADS-CFT correspondence, the ER equals EPR conjecture, the black hole information paradox, holography, lots of these other kinds of things. This is both a very broad and a very deep mathematical structure, and kind of the objective for these for the next few lectures is to give you a sense of, of kind of what the key ideas are. I'm aware that there are many of you who come from various different backgrounds. We have mathematicians and physicists and computer scientists and other people from at all kinds of different levels. So inevitably, I will end up saying some things that many of you will know very well. I may also say some things that many of you will find completely inscrutable. There's not a huge amount that I'm going to try to do my best to make this as interesting and as accessible to everyone as I possibly can, but that's kind of an impossible task given the diversity of the audience. But the hope is that the discussion sessions that we run after the fact will help you to clarify. Well, hopefully, for those of you who find these lectures boring, will help you to kind of engage a bit more with the material. And for those of you who find them totally confusing and alienating, will help you to kind of to allay some of your confusions. But we'll see how well that goes. Anyway, that's enough of the vision. Let me get into the actual content. So I mentioned, the key idea is could treat space as a very large collection of discrete points that on a large scale resembles continuous space in much the same way as a large collection of discrete molecules resembles a continuous fluid. So back in the NKS days, Stephen proposed a way of doing that in terms of what are called trivalent networks. Here are some examples here. So a trivalent network is just an ordinary regular graph where every vertex has degrees 3. The reason for choosing trivalent networks is because they're a universal graph representation. Because if you have any arbitrary network, you can take that arbitrary network and you can replace it with something that's a trivalent network, but has the same large-scale combinatorial properties. Because basically any vertex that has a degree greater than 3, you can replace that with a cycle of vertices that have degree exactly 3, and then let's say the large-scale property of the network is the same. So then, here's an example of an evolution for one of those trivalent networks that produces effectively a Sierpinski tetrahedron. This is a geometrical structure that we'll see many, many times during the course of the next few talks. And so this represents a possible dynamics for a simple universe. This is obviously so simple that it couldn't possibly be our universe. But as we saw on the previous slide, there's great diversity out there, even amongst very simple network transformation rules. One of the problems with the trivalent network approach, though, is that Stephen discovered was that there are some sort of technical issues when you try and define dynamics, because so amongst other things, it becomes a little bit tricky to figure, if you do a subgraph replacement, it becomes a bit tricky to figure out how you kind of plumb the replaced subgraph back into the rest of the network. And effectively, you have to have the situation where the symmetry group of the outgoing hypergraph has to be at least as large as the symmetry of the incoming hypergraph, as well as preserving the number of outgoing edges, because otherwise, if the symmetry group is reduced, then there isn't a unique way to kind of plumb the resultant hypergraph, the resultant subgraph back into the rest of the trivalent network. So as a result, more recently, we've been investigating an abstract generalization of this framework, considering not trivalent networks, but actually arbitrary hypergraphs. So what is a hypergraph? Well, okay, a hypergraph is it's a generalization of an ordinary graph in which one has hyperedges that can connect any arbitrary subset of vertices, any arbitrary non-empty subset of vertices. So set theoretically, you can think of a hypergraph as just being a collection of ordered relations between abstract elements. So on the left here's an example of a hypergraph corresponding to a collection of arity2 relations, binary relations, which can therefore be interpreted as an ordinary directed graph. On the right here is a collection of arity3 relations, which can therefore be interpreted as a hypergraph in which each hyperedge connects an ordered sequence of exactly 3 vertices. So these are the sort of fundamental structures that we're trying to investigate. So then you define a dynamics on these hypergraphs by saying, basically, if you have a piece of the hypergraph that looks like this, then you can replace it with a piece of the hypergraph that looks like that. And this having this general formulation in terms of set substitution systems, where you're basically saying, if you have a collection of ordered relations between elements and it contains a subset that matches a particular pattern, then replace it with a subset matching a different pattern, that the generality of that construction means you get around a lot of these symmetry problems that you would otherwise have in these more constrained trivalent network models. So effectively, each such updating rule, each such hypergraph transformation rule or set substitution system defines a different candidate dynamics for the hypergraph. So then if you just take a simple initial hypergraph like this sort of double self-loop here, and you apply the, for instance, this particular transformation rule in all of the places where it applies, effectively trying to update every hyperedge simultaneously without overlap. So you construct kind of the maximally non-overlapping sequence of update operations, then you get an evolution that looks something like this. And so then, so here it is after 10 steps of evolution, after 14 steps of evolution, you get this more complicated looking thing here. And at a large scale, many classes, many instances of these hypergraphs have kind of effectively bulk geometry that is quite like the geometry of Riemannian manifolds. In fact, in certain cases, we can prove are exactly the geometries of Riemannian manifolds, which is one of the things I want to sort of discuss in the course of these lectures. So this is the underlying model that we're investigating as a candidate for a model for our universe. Now, obviously, at first, it seems a little bit crazy that something this simple could actually reproduce anything like existing physics. What I want to try to convince you of today is that a major feature of our universe, namely special relativity, emerges as a very natural consequence of these hypergraph rewriting systems with things like general relativity and gravitation and other things, which I'll discuss tomorrow, I think. I forget when my next lecture is, but I think it's tomorrow morning. Okay, so one concern that you might very reasonably have if you're presented with this formalism is what is the canonical updating order for one of these models, right? If you're presented with a hypergraph like that and a replacement rule like this, then there are canonically many possible places where that rule could get applied, and each place where you apply the rule will place constraints on other places where you could apply the rule, and so each sort of initial choice of updating event corresponds to a different choice of updating order. And in general, different choices of updating order will lead to distinct kind of non-isomorphic spatial hypergraphs. And that's sort of a problem because it means that, that in effect, you won't have deterministic evolution of the system. So the first question you might ask is, well, how do we get around that problem? So that's what I kind of want to discuss here. So it turns out, the main thing that's kind of observationally accessible is not the hypergraph itself, but the sequence of, the particular set of causal relationships between the updating events. So what matters is the sequencing of events in time, as opposed to the strict kind of space-like separation of the events themselves. So in other words, given a sequence of applications of updating events, we can ask which updating events, are causally dependent on which other updating events, or in other words, if you applied a rule at a particular place and you call that event B, could event B have been applied if a previous event A hadn't already been applied? So to represent those causal relations, we construct this thing called a causal network, which is a directed acyclic graph where the collection of vertices is the collection of updating events, and in which each directed edge between vertices A and B exists if and only if event B could only have been applied if event A had previously been applied. And so from a kind of pragmatic point of view, the way we can work that out is we say if the input for event A has a non-trivial overlap with the output of event, the input for event B has a non-trivial overlap with the output of event A, then we know that there's a causal relation, because effectively that's saying the input for event B is making use of nodes that were produced by the output of event A, and therefore obviously event B couldn't have been applied unless event A had been applied. And so then you construct effectively a causal partial order, and then the causal network you can think of as being the Hasse diagram, or the transitive reduction of the Hasse diagram for that causal partial order. And so you get this thing that looks like this. So each one of these pale yellow boxes here is a representation of an updating event that's transforming one subhypergraph into a different subhypergraph. And each orange edge is denoting a causal relationship between those updating events. So we know this event couldn't have been applied unless this event and this event had both previously been applied. And so the speculation, the suggestive speculation, is that this causal network, or its transitive reduction, corresponds to the Hasse diagram for the causal partial order on some discrete approximation to a Lorentzian manifold, just like you can define a causal partial order in ordinary general relativity by considering the sort of topological properties of Lorentzian manifold. And so that, again, that's something we're going to discuss in a minute. So then really the question about what about all of these different choices of updating order? How do you get around the fact that there are many canonical choices of updating order? That question effectively becomes, how do we guarantee that the causal network, the particular causal partial order that we see, is always unique, is always the same? So because there are many different possible evolution histories, generically, you won't see a single thread of evolution. You'll see a non-deterministic evolution where effectively the universe bifurcates at all these different places, and there's actually a whole directed acyclic graph, or a merging tree that sort of parametrizes all of the possible evolution orders. So this produces a thing that we call the multi-way evolution graph, which you see here. So every blue node here is a specification of a hypergraph. Every gray edge is an application of an updating event. And so the multi-way evolution graph is parametrizing the set of all possible updating orders that you could apply to that hypergraph and showing what you obtain. And of course, the merging criterion for two nodes in the multi-way evolution graph is the isomorphism of the underlying hypergraphs. So given that the evolution is actually not a path, but rather this directed acyclic graph, how can we possibly get deterministic behavior? Well, Okay, this is illustrating a particular choice of path, a particular choice of updating order, which actually is the choice of updating order that we saw here. So there is nothing particularly special about this particular choice of updating order. It's just some random updating order we picked that happened to be valid and non-overlapping and consistent with the causal partial order. But you can see there are also all of these other different valid updating orders that will yield different non-isomorphic spatial hypergraphs. And again, skipping ahead a bit, the statement that there isn't a canonical updating order for these Wolfram model systems corresponds in the relativistic case to the statement that there is no canonical reference frame in our universe. Okay, so the way we get around this is by imposing this property that we call causal invariance, that, as I say, is a really fundamental thing that it's quite important to understand if you really want to kind of get your head around what these models are doing. Before I can really explain causal invariance, I'm going to introduce a bit of sort of terminology and machinery that comes from mathematical logic, and particularly from an area called abstract rewriting theory. So in abstract rewriting theory, an abstract rewriting system, or an ARS, is just a set, which we'll call A, where every element is an object, and a binary relation, which we'll call arrow, which is known as the rewrite relation. And so the intuition is, in the case of a Wolfram model system, if we formulated it as an ARS, the set of objects would be, the set A would be the set of all possible hypergraphs, and the rewrite relation is the specification that a particular hypergraph can be rewritten as a different one using a particular rule. And so in this case, each directed edge in the multi-way evolution graph corresponds to an instance of this binary rewrite relation of the ARS. So given that rewrite relation, we can define its reflexive transitive closure, which we'll call arrow star. In other words, it's the transitive closure of the union of the rewrite relation with the identity relation. And so what that's saying, if you say, okay, so as I say, if you say A arrows B in the Wolfram model case, that's saying hypergraph A can be directly rewritten as hypergraph B. If you say A arrow star B, that's indicating that either A and B are isomorphic, or there exists not a single updating event, but actually a finite updating sequence, a sequence of updating operations that connects A to B. So in other words, we could say that this hypergraph arrows stars this hypergraph because there exists this finite rewrite sequence that connects one to the other. Or to be a bit more precise, this vertex lies strictly in the out component of this other vertex. That's what the reflexive transitive closure is. So it's the smallest preorder that contains arrow. So it's a binary relation that satisfies both reflexivity and transitivity and is kind of minimal with respect to those properties. Okay, so then given that, we can introduce this concept in mathematical logic called confluence. I think in older mathematical logic texts, it's known as the Church-Rosser property, because I think Alonzo Church and J. Barclay Rosser proved it for the case of untyped lambda calculus back in 1936. But essentially, confluence intuitively gives you this idea that the order of application doesn't matter in some very precise sense. So what it means is that for any bifurcation that you see in the multi-way evolution graph, like this bifurcation here, there is eventually a resolution, as you can see in when these two hypergraphs, that hypergraph there and that hypergraph there resolve to yield this hypergraph here, we could describe this element as being a confluent element or a confluent object. Because anytime there's a bifurcation, anytime there's a rewrite sequence leading from A to B and A to C, there's also a common element D in their kind of future light cone to which both B and C resolve. And so if all of the elements in the rewrite system are confluent, then we can say that the overall system is confluent or has this Church-Rosser property. So here's an example of a multi-way evolution graph for a system that we can immediately see as confluent, is globally confluent, because you can see that for every bifurcation, they eventually resolve back to a common element within a single step. Now, there's no requirement that they resolve back within a single step. They could take arbitrarily many steps to resolve. This is why the problem of determining confluence of an arbitrary multi-way system is hard. In fact, it's provably undecidable in the general case. But nevertheless, in certain simple cases, like in the case of one-step convergence, we do have ways of determining it. Okay, so global confluence, as I say, is one very precise sense in which we could say, if you have a globally confluent rewrite system, the order of application of updating events doesn't matter. The interesting thing is that confluence is a sufficient condition. Confluence is a necessary condition. For this much more general and powerful property that we call causal invariance. So causal invariance is the statement that all of the causal networks that get generated by each branch of the multi-way evolution graph ultimately end up being isomorphic as directed acyclic graphs. So in other words, it kind of doesn't matter which updating order you choose. The causal network you end up with is always unique up to isomorphism. So not only is confluence a necessary condition for causal invariance, but moreover, and perhaps more excitingly, causal invariance is a sufficient condition for Lorentz symmetry, which of course is the basis of special relativity. And so the basic idea is whenever you have a causal invariant rewrite system, a causal invariant Wolfram model system, you immediately have satisfaction of special relativity. And I'm going to walk you through basically how that argument works. By the way, the claim that confluence is a sort of necessary condition for causal invariance, that's a pretty sort of, I think that's a pretty instructive exercise to do. I think, gave some hints about how to do it on Slack. But yeah, the basic idea is if you consider the kind of base case in which you have an elementary bifurcation in the multi-way system, and then demonstrate that the causal networks you get for the bifurcation that doesn't sort of reconverge, if you show explicitly just by computing it that the two causal networks you get out are non-isomorphic, then you can prove the claim in general. Given that base case, you can prove the claim in general by just doing strong induction on the set of all possible updating events. Like I say, I highly encourage you to do the exercise if you want to kind of figure out, if you want to get better intuition for the relationship between global confluence and the property of causal invariance. So, okay, to make that a little bit less abstract, here's an example of a multi-way system where you can explicitly see this correspondence. So this is a multi-way causal network now. So you can see we have updating events in yellow connected by causal relations in orange, but we also have states, i.e. individual hypergraphs that we color in blue, connected by evolution edges that we color in gray. And so in this particular case, you can see the system is confluent because when you have a bifurcation, it immediately kind of reconverges. In fact, we know that it's one-step confluent. But moreover, we can see that it's actually causal invariant because by just explicitly tracing out each path, you can see that for the 4 possible evolution paths through the system, the causal network you get out, the particular sequence of causal relationships that you observe, that you kind of peel off from the system, are always the same. In fact, in this case, they happen to be always trivial. They're always just path graphs consisting of 4 updating events connected by 3 causal edges. Okay, so that's a bit about the sort of the correspondence between global confluence and this property that we call causal invariance, the property that the causal network is always unique, independent of the updating order. There are a bunch of, I happen to formulate this in terms of this particular field of mathematical logic, which is abstract rewriting theory. There are a bunch of other ways you can formulate effectively the same idea. I'm not really an expert in category theory, but there is I know enough to be able to kind of figure out a basic category theoretic representation of the same idea. So if you think about this rewrite relation arrow, if you think about it instead as being an indexed union of subrelations, then what you end up with is this computational object, which is a labeled state transition system. And so that system is then a bijective function from the set of objects in the rewrite system to the power set of that set of objects, i.e., the set of all possible subsets that's indexed by the labels. And so then what you end up with is this thing called an F coalgebra for that power set functor. But again, let me not go into too much detail into the sort of precise category theoretic formulation, although I'm happy to discuss it with any of you who kind of know a bit about category theory. I mean, but the basic idea being then once you have a categorical representation of the multi-way evolution graph, and in particular, when you think of the rewrite system as being an endofunctor on the category of sets, then effectively what happens is the statement of global confluence becomes a statement that for every cone in the associated category, there is a corresponding co-cone, which corresponds to the statement that anytime there's a bifurcation in the multi-way evolution graph, there's an associated convergence. And so I'm just trying to illustrate that there are a few different ways you can formulate the same idea of confluence, but they are all kind of ultimately formally equivalent. Another way you can think about the same idea, as I mentioned, is in the context of this thing called the untyped lambda calculus in computability theory. So again, for those of you who know about lambda calculus, when you do beta reduction and you replace the bound variables you get by doing alpha conversion, if you then replace them in the body of the abstraction, you get effectively a rewrite operation between lambda terms, and then the statement that 2 lambda terms are equivalent becomes itself equivalent to the statement that the 2 lambda terms are joinable in the sense that there exists a common lambda term to which the 2 lambda terms x and y are both reducible, and that's again a statement of convergence between bifurcations in a multi-way system. And so the claim that the claim that lambda calculus exhibits the Church-Rossa property is exactly the claim that this rewrite system satisfies global confluence, and therefore subject to some additional assumptions is also a causal invariant system. So the main thing I kind of want to get across in saying all of that is that causal invariance is a very general property of computational systems. It's not specific to hypergraph systems, but in our case, where we're considering hypergraph systems, it happens to be of great interest because of its relation to special relativity. Again, these are some ideas that I'll discuss in more detail in the quantum mechanics lectures because they turn out to be very, very important for our understanding of quantum mechanics and in particular of quantum measurement. And in understanding the relationship between quantum mechanics and special relativity. But in addition to global confluence, which I already described, there are several modifications to that property. So you could consider a concept like local confluence, where you're saying any divergence that happens after a single step have to converge after an arbitrary rewrite sequence. That's a kind of weaker form of global confluence that's only equivalent to local confluence and global confluence have equivalence when the system is fairly simple, but in more complicated systems when you don't have guaranteed termination, they become quite different. Then there are also concepts like semi-confluence, where effectively one of your elements of the bifurcation is produced by a single updating event and the other is produced by an arbitrary sequence of updating events, and again they're forced to converge. There are also ways you can strengthen the property, like the strong diamond property, where effectively every bifurcation has to reconverge within a single step. We actually saw an explicit example of that here. This is an example of a rewrite system that's not just causal invariant, but it also satisfies the stronger condition of the strong diamond property. And things like strong confluence, which is the property that when you have objects diverging after a single rewrite operation, at least one of them has to converge after no more than one additional rewrite operation. That's weaker than the strong diamond property, but still stronger than global confluence. Anyway, again, that's kind of an aside. I just kind of wanted to place those ideas in your head in kind of preparation for the quantum mechanics lectures, because we'll discuss that in much more detail then. So here's the basic point. Okay, so different choices of updating orders are effectively are different choices of which updating events you want to apply. And so in particular, as I say, when you want to evolve the system in time, you want to apply the maximally non-overlapping set of updating events, the maximally sort of non-overlapping space-like separated set of updating events on the hypergraph. But generically, there are many such possible choices. There are many possible choices of updating order. So each one of them you can think of as corresponding to a different foliation of the causal network, because as I say, the causal network consists of these updating events that are the vertices and these causal edges that are the causal relations that are the edges of the causal network, the relations in the partial order. And so by foliating the causal network, by splitting it up into an equivalence class of different updating events that are considered to be simultaneous with respect to some observer, each possible choice of foliation corresponds to a different possible choice of of sort of consistent space-like separated updating events, space-like separated updating events that are non-overlapping and therefore consistent with the causal partial order. And so the statement of causal invariance therefore becomes the statement that the combinatorial structure of the causal network is invariant under different choices of foliation. So here's a particular choice of foliation with a particular sequence of hypergraphs that you see, as seen by this particular observer. Here's a different choice of foliation that's still perfectly valid. It's a perfectly, it's still consistent with the causal partial order. And so it's another valid choice of updating order for this particular hypergraph rewrite system. But you can see it produces a different sequence of hypergraphs. So in particular, like here, the third hypergraph you see in this rewrite sequence is clearly non-isomorphic to the third hypergraph seen in this rewrite sequence. But nevertheless, because of causal invariance, we know that independent of the updating order, the structure of the causal network, its pure combinatorial structure, is always the same. So the causal network is unique up to isomorphism. So as I mentioned, because you can think of the causal network as being like a representation of the causal structure, the conformally invariant structure of some Lorentzian manifold, what we're really saying is that the causal network because the causal structure of such a manifold is exactly the conformally invariant structure, and because causal invariance is saying that combinatorial structure is unique under any parameterized change of observer, under any parameterized change in the choice of updating order, what you end up with is the statement that effectively the combinatorial structure of the causal network is invariant under the action of the conformal group. And so because both the Lorentz group and the Poincare group are subgroups of the conformal group, one immediately determines that one has both Lorentz symmetry and Poincare symmetry, both of which are important for special relativity and general relativity, respectively. In fact, we've actually shown a slightly stronger thing. It turns out, and again, this will be a topic that we cover in the general relativity lecture tomorrow, but not only is causal invariance sufficient for proving Lorentz symmetry, it's also sufficient for proving local Lorentz symmetry, and in fact, weakened versions of the principle of general covariance, which is kind of the basis of the general relativistic derivation. Okay, so that's the high level picture of how special relativity works in the context of these models. It's just a sort of an immediate consequence of the principle of causal invariance, of the principle that the causal structure of the discrete approximation to the manifold is invariant under different choices of foliation and different choices of observer. one concern that you might have that's a purely kind of mathematical one is we did a bit of sleight of hand here by introducing this notion of a causal network foliation without really explaining what it is. As I say, it's an equivalence class of different updating events in the causal network, that's ordered in time. But to be a bit more precise, what we're doing when we construct these foliations is we're assuming that the causal network is associated to what you might call a globally hyperbolic spacetime. In other words, we're assuming that there exists a universal time function, which we'll call t, that effectively maps from the updating events in the causal network onto integers that correspond to the particular layer of the foliation on which that updating event lies, such that delta t is non-zero everywhere. In other words, such that these space-like hypersurfaces don't sort of trivially intersect. There has to exist at least one causal edge between a particular updating event on one hypersurface and the kind of corresponding updating event on the neighboring hypersurface. And we're also saying that this choice of universal time function effectively foliates the causal network into a parametric family of non-intersecting space-like hypersurfaces, which are the level sets of that universal time function. So each one of these things here you can think of as being the level set of the function that's mapping updating events in the causal network onto values of the universal time function. So then to really understand how, what these foliations are and how we can parameterize them and how we can think about them, we make extensive use of the techniques of geometric quantization in canonical Hamiltonian quantum gravity. And so there's this concept that exists in canonical sort of Hamiltonian GR, which is of the ADM decomposition, the ADM formalism, where the basic idea is the way you parameterize you take your Lorentzian manifold, your spacetime manifold, and you foliate it into the level sets of this universal time function. And then locally, the way you describe that foliation is by making a gauge choice. And it turns out we can make a discretized version of exactly the same gauge choice that one does in standard ADM relativity in the context of these causal networks. So essentially what you have to note is that the hypergraph comes equipped with essentially a natural distance metric, a combinatorial distance metric. So any two nodes that appear in the hypergraph, they will naturally be separated by a certain number of hyperedges. So you can define a delta L, effectively a norm between those sorry, not a norm, a metric between those hypernodes. That is the number of hyperedges one has to traverse to get from this part of the hypergraph to this other part of the hypergraph. And so in doing that, one is effectively implicitly defining a kind of discrete spatial metric tensor, which we can call gamma ij in terms of this natural choice of metric delta L. And this gives us a natural coordinatization, or at least a local coordinatization of the hypergraph. And moreover, one also has a coordinatization of the actual time evolution, because we can define time, we can define lapses, we can define intervals in time, just in terms of, if you want to know the interval of time between two updating events in the causal network, you can just count the number of causal edges that separate them in some path. And so effectively what you can do locally on each hypersurface is define a discrete lapse function that tells you effectively how many causal edges do you have to traverse between this updating event and the next updating event. And you can also define a shift vector that tells you effectively, so the lapse function is effectively giving you the time-like distance, the time-like separation between the local parts of those two hypersurfaces. And then you can also define a shift vector that tells you effectively the space-like separation. So what you're really asking is, what is the natural distance on the hypergraph between the place where this updating event got applied and the place where this future updating event gets applied? And so by defining a discrete lapse function and a discrete shift vector for every updating event on the current foliation of the causal network, you completely determine the future foliation of the causal the next hypersurface in that particular foliation. And so by taking all points in space-time, all points on the causal network, and assigning them a discrete lapse and a discrete shift, we successfully parameterize the complete foliation of the spacetime, and therefore, the complete specification of the observer. So by analogy to ordinary general relativity, you can think of this particular gauge choice is the gauge choice being made by a local normal observer, an observer moving with respect to geodesic normal coordinates in the flow of time. And so by combining these together, so this is our specification of the relationship between the spatial coordinate system and the shift vector beta. This is the relationship between the time coordinate system and the lapse function alpha. And so together they give us an overall line element, a space-time line element for the overall causal network that looks like this. It's this discrete line element with this particular form. So that's that's effectively what we're doing when we talk about these causal network foliations. Each foliation, as I say, is a particular choice of updating order corresponding to a particular choice of observer, and where the choice of observer can effectively be parameterized by making a local gauge choice of lapse function and shift vector at every point in space-time. Okay, so this also, one important thing that I really ought to say is, I could kind of leave the derivation there, right? It's all the pieces are kind of in place. So you know that the system we are dealing with is causal invariant. So there is a unique causal network up to isomorphism, and so under any parameterized change of observer, the combinatorial structure of the causal network is always the same. And so in particular, what you're really saying is, even though the ordering of space-like separated updating events can change, the ordering of time-like separated updating events is always preserved, which is precisely the statement of Lorentz symmetry. And so and furthermore, the statement that the hypergraph replacement rules have fixed size, and so you can't get propagation of information faster than the hypergraph itself can evolve, gives you a natural speed of light. And so you immediately have the two fundamental postulates of special relativity, and we have everything we need to prove local Lorentz symmetry, which, as I say, just kind of trivially follows from the principle of causal invariance. So I could kind of leave the derivation there, but in the interests of not being totally obscure, let me actually give you a little bit more detail about how you can see a kind of toy case of this for yourself, kind of in a more explicit way. I should mention that this derivation of the more explicit case this is very much a toy example. It's a naive example. It only works in certain numbers of dimensions, and it requires a sort of an embedding algorithm that doesn't generalize. But doing this derivation in the general case, as I say, effectively requires considering the action of the conformal group in the way that I just described. So what if we consider now, we take a causal network and we just make a really, really naive choice of norm. So what we're going to do is we're going to take the causal network, we construct a layered digraph embedding so we're taking this directed acyclic graph, we're constructing a layered embedding into the plane, which we can do because we know that the system is globally hyperbolic. And so if it's globally hyperbolic, we know that there don't exist closed time-like curves, and so that, there's no place where the layered digraph embedding is going to fail. So in other words, we guarantee that we can embed the directed graph in such a way that all of the causal edges point monotonically downwards. So given that layered embedding, you can then induce a geometry. So you can think of that embedding as being an embedding into some lattice Z1n. And given that embedding, you can make a sort of a very naive choice of norm, which is just the space-like distance, the natural hypergraph distance squared minus the time-like distance squared. So in other words, between any two updating events, you can just compute what is the distance, this distance in the spatial hypergraph between the places where those updating events got applied, square it, and subtract the time-like separation, the causal edge distance between those two events in the causal network, and you immediately get a very naive kind of discrete approximation to the Minkowski norm with respect to this space. And then, of course, we immediately get a sort of a classification of events. We can classify events as being time-like, light-like, or space-like, depending on whether their sort of discrete Minkowski norm is negative, 0, or positive, respectively. And then that of course, corresponds exactly to the sort of intuition we have about these causal networks, that a pair of updating events are time-like separated or causally related if and only if they are connected by a finite path with respect to the causal network. They are light-like separated if they're time-like, but somehow extremal, so that they lie on the boundary of a light cone rather than on the interior. And again, we can show some explicit examples of exactly what that means in a minute. And that they are space-like separated if they're not light-like or time-like. So in other words, these events here are space-like separated because they're not directly connected by any path in the causal network. There's no causal dependence of this event on that event, and that's why we're allowed to construct a foliation in which we consider those causal events, those updating events, as being simultaneous events being applied to the spatial hypergraph at the same time without any kind of overlap or violation, because that choice of local updating order is still consistent with the causal partial order. Okay, so like I say, then based on whether the normed distance between a pair of updating events is time-like, light-like, or space-like, you then immediately get this notion of time-like, light-like, and space-like separation. The particular choice of foliation, and therefore the particular choice of layered digraph embedding, sort of trades off which parts of the multi-way Minkowski norm are treated as being spatial parts and which parts are treated as being time-like parts, and so that then that means therefore that the structure of your light cones locally is dependent on the foliation, as we'll see in a minute. So then this gives us another way. Once you have the notion of the embedding of the causal network into this lattice, and then you have this notion of a very naive Minkowski norm defined on it. This gives us a different, a more concrete way of thinking about what these space-like hypersurfaces are. We can think of them as being like the discrete analog of Cauchy surfaces for a time evolution problem. So in other words, they're a set of updating events, so that every time-like or light-like path, effectively every finite path in the causal network consisting of events connected by causal edges, intersects an updating event that exists in that surface exactly once, which is another way of saying that the system is kind of locally hyperbolic, so that you don't have kind of loops or weird situations where the path kind of stays on the hypersurface for a bit and then diverges out. If it's globally hyperbolic, everything is pointing monotonically downwards, and so you can guarantee that this this Cauchy surface has every time-like and light-like path intersecting it exactly once. And so this is a more formal way of saying that it's a locally hyperbolic kind of a hypersurface existing in the foliation in which every pair of updating events is strictly space-like separated. So given that given that notion of a Cauchy problem with respect to the causal network, we immediately get all of the standard differential topology techniques that come from general relativity and that come from the analysis of Lorentzian spacetimes and so on. This whole concept of causal structure of a Lorentzian manifold, we can kind of import all of those techniques from ordinary general relativity to the discrete case of our causal networks. And and because the causal partial order of our causal network is really a discrete approximation to the causal partial order of a continuous Lorentzian manifold, unsurprisingly, all of the properties of causal structure and conformal structure sort of naturally port over to the causal network case. So in this instance, we can say if there exists a chronological path but connecting a pair of updating events in the causal network, then that is future directed, so in which every causal edge points monotonically downwards, then we can say that one of those updating events strictly chronologically precedes, or one of those updating events, for the case wait, sorry, I've mistyped this. This should say causally precedes. I got confused for a moment. Yeah, so in the case where there exists a chronological path, i.e. a path consisting of purely of sequences of causal edges that lie within a light cone, then we can say that one of those updating events chronologically precedes the other. We can say that one strictly causally precedes the other if there is a non-space-like path. So in other words, if there's a chronological path or a time-like path, a chronological path or a light-like path that exists at the boundary of the light cone that connects those updating events. And we can say that it non-strictly causally one event non-strictly causally precedes the other if either one strictly causally precedes the other or the two updating events are actually equivalent. So that gives us a way of defining essentially a conformal structure on the causal network. And then all the properties that are so difficult to prove in standard general relativity to do with causal and conformal structure, like the fact that the fact that both chronological and causal precedents are transitive, that becomes an immediate consequence of the fact that the causal network, as I said right at the beginning, is a transitive reduction graph. So in which effectively one has transitivity more or less axiomatically. So then, given a notion of chronological future, chronological past, causal future, causal past, you can introduce notions of the future and past of individual events. So unsurprisingly, if you pick an updating event in the causal network, you can think of its chronological future as being the set of all updating events that you can reach by a finite sort of time-like path, or chronological evolution path. Following on from that updating event, its chronological future is the set of events that exist sort of in its past light cone. And so with respect to the causal network, you can define all of these properties purely combinatorially. So if you, in other words, if you pick an updating event, its total future light cone, so in other words, the combination of its chronological and causal future is just the vertex out component of that causal vertex, and the union of its chronological and causal past is simply the in component of that particular causal vertex. And so concepts like future and past light cones become really very, very easy to sort of represent using this combinatorial structure. So if the chronological future is sort of strictly the interior of the light cone, of course, the causal future is both the interior and exterior. We can define that both for individual updating events in the causal network X. We can also define it, of course, for finite collections of updating events, in which case we get a whole collection of updating, a collection of light cones as opposed to just a single light cone from a single event. So as I say, you can think of the chronological future I plus as being purely the interior of the cone, and the causal future J plus as being both the interior and the boundary of the cone. So here's an explicit example of a future light cone that you can construct in a causal network. In this case, not for a hypergraph substitution system, but actually for a simpler one-dimensional string substitution system. So here we pick an event like this, and we just say, what is its out component? We can just color all of the vertices in the causal network that are in the out component. And then we can say, okay, all of the paths in this causal network that are extremal, that effectively lie at the boundary of that out component, we can think of as being those are effectively our light-like paths. Those are the boundaries. Those are the things that are included in the causal future. And then the strict interior, those are our evolutionary paths. Those are our chronological paths. And so those aspects correspond to the chronological future of the updating event, but are not part. But the things lying on the boundary are not part of the chronological future of that event. So this is the case. This is an illustration of the case for a future light cone. For the case of a past light cone, it works in much the same way, just with the edges flipped around. And again, just like we have the standard algebraic properties of causal and chronological precedence, we also have the standard algebraic properties of causal and chronological future, which again hold sort of combinatorially. So because we more or less define the chronological paths as being a strict superset of the set of all causal paths, again, this is another example of a claim which is quite hard to prove in differential topology, but which holds more or less trivially in the case of a causal network. So given that, we have a more precise way of talking about both the foliation of the causal network and a more mathematically formal way of describing what it means for the system to be globally hyperbolic, and therefore for it to have a well-posed Cauchy problem. So we can say, if given a particular a collection of updating events, then you can take the set of all the updating events in which all the past directed causal paths, so in all the past directed paths that are either chronological or light-like, intersect an updating event that lies in that set at least once. That gives us the notion of a discrete future Cauchy development. And again, if we consider the same but with past change to future, then this gives us a notion of a discrete past Cauchy development as well. And then the discrete Cauchy development for a particular set of events is then the union of the future and past Cauchy developments. So if you're given a space like a hypersurface in the causal network, if you're given a particular sort of collection of updating events that are considered to be space-like separated, then you can construct a Cauchy development with respect to that particular collection of events, just like you would in ordinary relativity. And so then a Cauchy surface, which is our notion of a space-like hypersurface, is then an achronal set of updating events whose Cauchy development is the whole manifold, is the whole causal network. And where achronal just means that the event is not in its own chronological future. So in other words, you can't have either closed time-like curves or degenerate cases of closed time-like curves where there are sort of causal edges that don't correspond to time evolution. And then, as I say, global hyperbolicity is then, of course, the statement that there exists a discrete Cauchy surface with respect to the causal network. So then I can flesh out in a bit more detail this argument about how, therefore, causal invariance implies Lorentz symmetry, even though, as I say, it's kind of a pretty elementary argument. What it's really saying is that because in standard differential topology, the causal structure of the Lorentzian manifold is invariant under a conformal rescaling. So in other words, if you take the metric and you apply a conformal factor omega, you get this new metric g hat, the time-like, null, and space-like qualities of each of vectors are invariant under that map. So in other words, the set of events that are considered to be space-like separated or time-like separated won't change. And obviously in special cases, when you consider purely inertial reference frames and so on, that immediately implies that, even though the space-like separations between events can change, orderings of time-like separated events don't change, which is precisely, because the causal edges correspond to the time-like orderings of updating events, is precisely the claim of causal invariance. So we have this very neat equivalence between the notion of the the manifold, the conformal structure of the manifold, or the causal structure of the manifold being invariant under a conformal transformation, and the causal network being invariant under parameterized changes of observers. So this is kind of in more detail, this is precisely what I meant when I said causal invariance is equivalent to the claim that the combinatorial structure of the causal network is invariant under the action of the conformal group, at least in some continuum limit. So why did I go through all the trouble of defining this very naive sort of discrete Minkowski norm? I will tomorrow in the general relativity lecture, I will go through in more detail how you can go about defining a less naive norm that doesn't depend on dimensionality assumptions and doesn't depend on an embedding in some lattice and all these other things. But the reason I wanted to give you at least a sort of a basic norm to start off with is because it then gives you a very nice intuition for how all of your favorite aspects of special relativity, like all the sort of standard physical consequences of Lorentz transformations start to emerge. So again, in ordinary special relativity, if you have two sort of inertial reference frames, F and F hat, and such that F is considered to be the sort of is the rest frame relative to which you're measuring velocities, F hat is moving at some constant velocity v relative to the rest frame, then you can define its direction of motion as some unit vector, and then its magnitude of motion is given by a hyperbolic tangent of this quantity rho. Which will sort of canonically rescale to be less than 1, corresponding to the statement that the velocity is subluminal. And then, assuming that the two coordinate frames are initially synchronized at the starting point, at the point where the time functions are the same, then the Lorentz transformation is the thing that gives you a way of expressing the coordinates on F prime in terms of the coordinates on F. And so because we have a coordinatization of the spatial hypergraph and the causal network, we can do exactly the same thing in our models. We can, given two particular choices of foliation of the causal network, we can construct the Lorentz transformation a discrete analog of the Lorentz transformation that rewrites the coordinatization of the F prime foliation in terms of the original rest frame coordinatization of the F foliation, so the Lorentz transformation looks like this. That gives us a way of translating between the coordinatizations corresponding to two different layered digraph embeddings of the causal network. So if we want to see an explicit example of how we do that, if you consider it as the basic two-dimensional case, let's think about this hypergraph rule here. This happens to be a very, very simple hypergraph transformation rule that constructs a simple one-dimensional hypergraph that then induces a kind of a very, very basic grid-like causal network, which you can think of as being like a kind of a 1+1 dimensional Minkowski space, which is therefore nice for doing analysis of special relativity. So this is the particular sequence of hypergraphs that one sees for the kind of canonical choice of updating order, for the default choice of foliation of the causal network that we can think of as being the foliation that was seen by an observer in a rest frame. If we now move to a boosted foliation, so effectively we take this causal network foliation and we tip it so that now we're considering different collections of updating events as being simultaneous. That corresponds to a different possible updating order. So we get something like this. And so for this updating order, you'll see, we see a different sequence of space-like hypersurfaces, and therefore a different sequence of spatial hypergraphs. So these two evolutions are different, even though they start and end with the same hypergraph. This one takes, I think, 14 evolution steps, where this one only took, I guess, 11 or something. I can't be bothered to count, something like that. Anyway, the basic point being, of course, just by sort of elementary causal network geometry, when you shift over to this tipped foliation, it takes more updating steps to move from the initial spatial hypergraph to the final one, because there are, effectively, because you're having to traverse more causal edges in the normal direction to your foliation in order to get from the initial hypersurface to the final hypersurface, which gives you immediately the relativistic analog of time dilation, which is not the relativistic analog, sorry, the discrete analog of relativistic time dilation, which of course is completely unsurprising, given that, as I say, what we're really doing when we construct these foliations is we're doing transformations between two choices of coordinatization, two choices of observer coordinatization that is compatible with the Lorentz transformation in the continuum limit of an arbitrarily large causal network. So here we have a way of constructing something like a Lorentz transformation that works in the discrete case, and in the continuous case where we take a limit as the causal network becomes arbitrarily large, it becomes precisely the ordinary Lorentz transformation. So this tells you, in some sense, why special relativity has to be true with respect to these Wolfram model systems. It's all just a consequence of causal invariance, of the invariance of the causal network under different choices of updating order. Okay, so I'm aware I don't have too much time left, so let me just cover quickly a kind of an amusing thing that is something that I don't know. I was kind of pleased to figure this out, but this gives you things like time dilation, length contraction, all those other features of the bulk features of space-time you can work out pretty easily from looking at these causal networks. One question you might immediately have is kind of what's the analog of relativistic time dilation in one of these systems? Sorry. What am I keep using the wrong words today. Not relative. What's the analog of relativistic mass transformation? So we've seen the time dilation case. What's the analog of the mass transformation? So that turns out to require something a little bit more abstract. So what you really have to realize, and again we'll discuss this in much greater detail in the general relativity lecture tomorrow, but the basic idea is that you can think of the energy momentum tensor in relativity as being, in our case, as being a measure of the flux of causal edges through in the causal network through a hypersurface of constant x nu. So this is the analog of the statement that energy momentum in relativity is the flux of relativistic momentum p mu through a hypersurface of constant x nu. Instead, if you pick a hypersurface in the causal network and you just measure how many causal edges are being fluxed through that hypersurface, that gives you a way of determining energy momentum with respect to one of our systems. And so then you can think of energy as being, energy or rest mass or something is related to the flux of causal edges through a space-like hypersurface, and momentum is therefore corresponds to the flux of causal edges through a time-like hypersurface. So then we can ask, well, how does that notion of energy change when we make these Lorentz transformations that correspond to that correspond to Lorentz boosts for observers and things like that? And it turns out it's compatible with relativistic mass transformation. The basic idea being, if you think about an elementary particle as being a sort of topological obstruction in the causal network or in the hypergraph, where in the toy case you can think of that as being like a non-planar piece of the network. So in other words, we know that there's this result in the foundations of graph theory, which is Kuratowski's theorem, which says that a graph is planar if and only if it doesn't contain a subgraph that's a subdivision of either K5, the complete graph on 5 vertices, or K33, the bipartite complete graph on 3 + 3 vertices. And so then that means that effectively every non-planar graph, its non-planarity can be reduced into a finite set of occurrences of K5s and K33s. And so turning that idea on its head, if you have a hypergraph transformation rule that preserves planarity, then if you have a non-planar structure, if you have a sub-hypergraph that is a subdivision of either K5 or K33, that will be preserved, and therefore it will behave effectively like an elementary particle. It will behave like a persistent topological obstruction. I need to clarify. This is not how we're saying particles actually work. This is just a very sort of toy model of this, much as the Minkowski norm is a toy model of how the actual norm works. This is a toy model of how particles might work. So this is an example. So this is the complete graph on 5 vertices on the right, and this is the bipartite complete graph on 3 + 3 vertices on the left. And so then if you consider a hypergraph that's associated with a hypergraph transformation rule that's preserving planarity, these lumps of K5s or K33s that contain irreducible non-planar crossings of edges will be preserved and will act like effectively elementary particles. And then what we want to know is how do the effective masses, in other words, how does the flux of causal edges through a space-like hypersurface change when we make a parametrized boost in the reference frame of the observer? Well, okay, like I say, it's a little bit abstract, but it turns out that the way you can derive relativistic mass transformation, and if I have time, I might go into a bit more detail about how this derivation works tomorrow, is in terms of these things called De Broglie indices. So in ordinary lambda calculus, when you want to avoid name collisions, you introduce these things called De Broglie indices. They're effectively ways of indexing generated variables in untyped lambda calculus. So if you consider the K and S combinators in combinatory logic, then because the De Broglie index, the numeral is giving you a sort of the number of binders that exist between the variable and the place where it got bound. So in this case, X has an index of 2 because there are 2 binders between this X and the place where it got represented. And in this case here, what is it? X has three binders separating this X from that one, and there is 1 binder separating this Z from that Z, and 2 binders separating this Y from that Y. So we get lambda, 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 3, 1, 2, 1. this is just the point of this is it's a canonical way of kind of labeling generated variables with respect to the lambda calculus. We can also use De Broglie indices as a way of labeling vertices with respect to these hypergraph systems. And in fact, that's effectively what we do when we have to deal with the case where there are generated vertices being produced by one of these set substitution systems. So then the basic idea is when you pick a boosted foliation through the causal network, that because you're applying more updating events, you're applying more rewrite steps, there are more generated variables that get produced. And so in just the same way as in an ordinary rewrite system, the generated variables aren't real. They're just kind of artifacts of the particular choice of rewrite sequence. In just the same way, you get a notion of generated hypernodes that are artifacts of the particular choice of updating order, particular choice of foliation. And so the more steep the boosted foliation, the more generated variables there are, because there are more applications of updating events, and therefore the heavier particles will appear to be, because they will appear to have more nodes associated with them, not because they actually have nodes associated with them, but because the nodes have appeared as an artifact of the updating order in much the same way as they do in the context of lambda calculus. And so that appearance of effectively generated variables as a consequence of the choice of updating order is the analog of relativistic mass transformation with respect to Wolfram model systems. Okay, just a final note before we get kicked out of the Zoom meeting for going over time. So I just wanted to mention one question you could have is, what's the difference between something like an inertial reference frame here and one of these crazy reference frames that we saw earlier, like this one that's effectively kind of that has arbitrary curvature where there's all kinds of weird gravitational interaction and so on. And effectively what it is, and maybe I'll discuss this, I'll leave the full discussion of this for tomorrow, but effectively the distinction between between an inertial reference frame and a kind of arbitrarily curved non-inertial reference frame is one of computability. And the inertial reference frame is corresponding to the reference frame as seen by a kind of arbitrarily computationally bounded observer, and where the curved reference frame is one in which the observer has to perform a kind of higher order computation in order to be able to determine what's going on. But I don't really have time to explain that comment in more detail here. Maybe we can discuss it in the discussion session just after this. But I hope to kind of go into more detail about that later. So I'm sorry if this went a little bit quickly, but I'm excited to get on. I wanted to cover kind of most of the toy cases of things here. Because I'm really excited to get onto the derivation of general relativity in tomorrow's lecture. That's going to involve, actually defining not just a toy case of a Minkowski norm, but a proper sort of space-time norm with respect to the causal network, and demonstrating how causal invariance implies not just Lorentz symmetry, but also local Lorentz symmetry. And therefore, by introducing a notion of curvature on spatial hypergraphs and on causal networks, we can derive the full form of the Einstein field equations and prove that sort of Wolfram model systems that are both causal invariant and which preserve dimension in the continuum limit, therefore have to be compatible with general relativity and gravitation. And we'll hopefully, if we have time, we'll look a bit at some of the sort of consequences that has for things like inflationary cosmology and other kinds of things. So I should probably, let me stop sharing and we can, I don't know how this, Erin, do we just shift to another room to do the discussion session?
It's on the lecture, or sorry, on the schedule. We will get kicked out of here in 4 minutes, so let's all go ahead and jump over if you want to do the group discussion for Wolfram Physics 1.
Sounds awesome. Okay, right. See you there.
Thank you.